Most people think weather comes from the sky. They're wrong. The greatest weather machine on Earth is not above your head, it is beneath it. Right now, thousands of kilometers from the nearest city, deep in the tropical Pacific Ocean, a vast body of water is quietly accumulating heat. Not a storm, not a hurricane, not a visible catastrophe, just heat. But that heat is capable of rearranging weather patterns across the entire planet, and it may already be happening. The next few months could bring floods where drought normally reigns, heat waves where temperatures should be mild, record-breaking rainfall in places that haven't seen it in years. Entire seasonal patterns may begin to behave strangely, as if the atmosphere itself has forgotten the rules. Because in a way, it has. The culprit is a phenomenon known as El Niño. And when El Niño becomes unusually powerful, meteorologists use a phrase that sounds almost harmless: Super El Niño. The name does not sound threatening. It should, because history shows that when the Pacific Ocean enters one of these extreme phases, the consequences can echo across continents. To understand why, you first need to abandon one of the most common misconceptions about weather. Most people imagine Earth's atmosphere as the main actor. Clouds move, storms form, rain falls, the sky appears to be in charge. But the atmosphere is more like a passenger. The ocean is driving. Earth's oceans contain over 90% of the excess heat trapped by the planet's climate system. Think about that for a moment. Imagine placing a small saucepan beside an industrial steel furnace. The saucepan is the atmosphere. The furnace is the ocean. One heats rapidly. The other stores immense amounts of energy. And when that energy shifts location, the consequences spread everywhere. The Pacific Ocean is especially important. Stretching across nearly one-third of Earth's surface, it is so enormous that changes occurring in one region can influence weather thousands of kilometers away. Meteorologists call these long-distance connections teleconnections. The name sounds technical. The reality is astonishing. A patch of unusually warm water near the equator can help determine whether California receives torrential rainfall. It can influence drought conditions in Australia. It can affect monsoons in India. It can alter hurricane activity in the Atlantic. It can even influence winter temperatures across North America. One ocean, one heat source, an entire planet responding. Under normal conditions, strong trade winds blow from east to west across the tropical Pacific. These winds act like giant conveyor belts. They push warm surface water toward Indonesia and Australia. Meanwhile, colder water rises near South America from the deep ocean below. This process is called upwelling. The result is a remarkably stable arrangement. Warm water piles up in the western Pacific. Cooler water dominates the eastern Pacific. The atmosphere adapts to this pattern. Rainfall develops where waters are warmest. Air circulates in predictable loops. Entire ecosystems depend upon it. Farmers depend upon it. Cities depend upon it. Billions of people depend upon it. Then El Niño arrives. The trade winds begin to weaken, sometimes dramatically. The giant conveyor belt starts slowing down. Warm water that was once trapped in the western Pacific begins migrating eastward. The Pacific Ocean effectively redistributes its stored energy. Imagine a gigantic bathtub stretching halfway around the planet. For years, water has been piled higher at one end. Then suddenly someone releases the barrier. The water rushes across the basin. The level changes everywhere. That is essentially what happens with heat during El Niño. And heat is energy. The atmosphere notices immediately. Warmer ocean water evaporates more rapidly. More water vapor enters the air. Cloud patterns shift. Jet streams move. Storm tracks relocate. Entire regions experience weather they were never expecting. This is why meteorologists pay such close attention to Pacific temperatures. A difference of just a few degrees Celsius across a vast ocean can initiate planetary consequences. The atmosphere is sensitive. The Pacific is enormous. Together they create one of Earth's most powerful natural climate oscillations. But occasionally El Niño becomes something far larger than normal. Occasionally the ocean doesn't merely warm, it overheats. Meteorologists define a strong El Niño by significant temperature anomalies across a large region of the central and eastern tropical Pacific. A super El Niño pushes those anomalies to extraordinary levels. The most famous examples occurred in 1982-83, 1997-98, and 2015-16. Each one left a global trail of disruption. Floods, Droughts, crop failures, wildfires, economic losses reaching tens of billions of pounds, and millions of lives affected. The 1997 to 98 Super El Niño was particularly dramatic. Sea surface temperatures surged far above average. Weather records fell around the world. Indonesia experienced devastating drought and wildfire outbreaks. Peru suffered catastrophic flooding. Coral reefs across tropical oceans endured widespread bleaching. The atmosphere seemed to enter a state of chaos. Yet, from a scientific perspective, nothing was chaotic. The planet was simply responding to a massive redistribution of heat. Energy was moving. Weather followed. And many scientists are watching the Pacific once again. Not because they know exactly what will happen. Nobody does. Weather is too complex for certainty. But they understand the ingredients. The ocean has been accumulating heat. Global ocean temperatures have reached extraordinary levels. Large regions of the Pacific are behaving unusually. The atmosphere is already showing signs of responding. And history teaches a simple lesson. When the Pacific begins rearranging its heat, the rest of the world rarely remains unchanged. This is the uncomfortable truth hiding behind forecasts and weather maps. What appears to be a local thunderstorm may actually begin thousands of kilometers away. What seems like a heat wave over your city may trace its origins back to a warming ocean basin larger than every continent combined. The weather outside your window is not merely local. It is connected. Connected to currents, connected to winds, connected to heat, connected to an ocean so vast that it can rewrite seasons themselves. And if a Super El Niño is beginning to awaken, then the weather patterns humanity has come to expect may soon start behaving very differently, because the ocean is moving, and when the ocean moves, the sky follows. The danger of a Super El Niño is not that it creates weather. The danger is that it amplifies it. The atmosphere already contains storms, already contains droughts, already contains floods. A Super El Niño takes those existing forces and begins turning the volume knob, sometimes slowly, sometimes violently. And history shows exactly what that looks like. If you want to understand what may be coming, you need to travel back to one of the most extraordinary climate events ever recorded. The year was 1997. At first, there was nothing obviously dramatic about it. No giant explosion, no asteroid impact, no visible scar across the Earth, just a gradual warming of the tropical Pacific, a few tenths of a degree. Then more. Then more. Month after month, meteorologists watched temperatures climb. Soon it became clear they were witnessing something unusual. The Pacific Ocean was entering one of the strongest El Niño events in modern history, and the consequences spread outward like ripples from a stone dropped into water. Only this stone weighed trillions of tons. By late 1997, weather systems around the globe were beginning to respond. Peru was among the first regions to experience the full force. Normally, the cold Humboldt Current helps regulate conditions along the western coast of South America. During the Super El Niño, warmer waters invaded the region. The atmosphere reacted immediately. Rainfall exploded. Areas accustomed to dry conditions suddenly found themselves drowning. Roads vanished beneath floodwaters. Bridges collapsed. Entire communities became isolated. Landslides thundered down hillsides. Infrastructure built for ordinary weather discovered it was facing something far from ordinary. Meanwhile, thousands of kilometers away, another disaster was unfolding: Indonesia. Under normal conditions, warm Pacific waters support rainfall across the region. But during a major El Niño, that warmth shifts eastward. The rain often follows. The result can be devastating: drought. In 1997, forests dried, peatlands dried, vegetation dried. Then fires began. At first they appeared manageable. Then they merged. Then they multiplied. Soon enormous sections of Southeast Asia were burning. Smoke spread across national borders. Air quality collapsed. Cities disappeared beneath a toxic haze. Satellite imagery revealed gigantic scars stretching across the landscape. Millions of people were affected. Economic losses climbed into the billions, and all of it traced back to heat moving across an ocean. That is one of the most difficult aspects of understanding El Niño. Cause and effect become separated by enormous distances. A farmer experiencing drought may never see the Pacific Ocean. A family facing floods may live thousands of kilometers inland. Yet their weather has become connected to events occurring far beyond the horizon. The atmosphere is Earth's messenger. The ocean writes the message. And During a Super El Niño, the message can become brutal. Australia experienced its own warning. Large portions of the continent endured severe drought conditions. Reservoirs shrank. Agricultural regions suffered. The already challenging relationship between Australia and water became even more precarious. For a continent where rainfall is often unpredictable, El Niño has long been viewed with particular concern, because Australians understand something many people do not. Rainfall is not guaranteed. Civilization depends on stability, and stability can disappear surprisingly quickly. But perhaps the most astonishing aspect of the 1997-98 event was its global reach. This was not a regional weather anomaly. This was a planetary event. Africa felt its influence. Asia felt its influence. North America felt its influence. South America felt its influence. Even the oceans themselves began changing. Coral reefs, some of the most biologically diverse ecosystems on Earth, found themselves trapped in unusually warm water. Corals survive within a narrow temperature range. Push temperatures too high for too long and a biological crisis begins. The coral expels the microscopic algae that help sustain it. The brilliant colors fade. The reef turns ghostly white, a process known as bleaching. During the 1997-98 Super El Niño, widespread coral bleaching occurred across tropical oceans. Entire ecosystems entered survival mode. Fish populations shifted. Marine food webs became stressed. What began as a temperature anomaly evolved into an ecological emergency. Then there was the atmosphere itself. One of the lesser-known effects of El Niño involves the jet stream. These high-altitude rivers of air guide storms across continents. Think of them as invisible highways in the sky. When ocean temperatures change, these highways can move. A slight shift in position may not sound important. In reality, it can completely alter where storms travel. Imagine moving a railway line by only a few kilometers. Every destination changes. Every timetable changes. Every journey changes. The jet stream behaves similarly. Storms that would normally miss a region may strike directly. Rainfall patterns can become distorted. Temperature extremes become more likely. Weather starts appearing unfamiliar, and unfamiliar weather often catches societies unprepared. The economic consequences can be staggering. The 1997-98 Super El Niño caused tens of billions of pounds in damages worldwide. Some estimates place the total far higher. Agriculture suffered, transportation suffered, infrastructure suffered, insurance industries absorbed enormous losses, governments faced unexpected emergencies. And despite all modern technology, humanity remained largely powerless to stop it. That is because El Niño is not a storm. You cannot build a wall against it. You cannot evacuate from it. You cannot switch it off. It is a planetary scale redistribution of energy. The atmosphere obeys, the oceans obey, humanity adapts or struggles to. Then history repeated itself. In 2015, another major El Niño emerged. Again, the Pacific warmed dramatically. Again, weather patterns shifted. Again, records began falling. Global temperatures surged. Many regions experienced extraordinary heat. Coral bleaching returned on a massive scale. Scientists watched as some reef systems endured severe damage. The event reinforced a growing concern. Super El Niños do not occur in isolation anymore. They now unfold against the backdrop of a warming planet. That matters. A great deal. Imagine adding fuel to a fire. The fire existed before. But now, there is more energy available, more heat available, more potential for extremes. Scientists continue studying exactly how climate change interacts with El Niño. Many details remain under investigation, but one reality is becoming difficult to ignore. The baseline is changing. Oceans are warmer, atmospheres contain more moisture, heat records are becoming easier to break. When a powerful El Niño develops under those conditions, the outcomes can become amplified, not because El Niño has changed, but because the environment surrounding it has changed. And that brings us to the present. Today, scientists monitor thousands of instruments across the Pacific. Satellites, buoys, ships, weather balloons. Supercomputers process unimaginable quantities of data. They track temperatures to fractions of a degree. They analyze wind patterns. They monitor ocean currents. They search for clues because they know what history teaches. A Super El Niño is never merely an ocean event. It is never merely a weather event. It is a planetary event. A chain reaction that begins in warm tropical waters and eventually touches farms, cities, forests, rivers, coastlines, and lives. The last time the planet felt one of these giants awaken, the effects reached nearly every corner of Earth, and the conditions now developing in the Pacific have many scientists asking a simple question: not whether weather will change, but how far those changes might go. To most people, the Pacific Ocean looks calm from space, a vast blue surface, silent, motionless, almost peaceful. But that image is an illusion. Beneath that surface exists one of the most powerful engines on Earth, a machine so large that it controls weather patterns across entire continents, a machine powered not by gears or fuel, but by sunlight, wind, water, and heat. And right now, that machine may be changing gears. To understand why a Super El Niño is capable of disrupting weather worldwide, you first need to understand how the Pacific normally behaves. Because under ordinary conditions, the Pacific is remarkably organized, almost disciplined. Imagine standing at the equator and looking west across the ocean toward Indonesia. Powerful trade winds blow steadily from east to west, day after day, month after month, year after year. These winds are among the most reliable atmospheric systems on the planet. For centuries, sailors depended on them. Today, climate scientists depend on them. Because these winds help maintain one of Earth's most important climate balances. As the trade winds push across the Pacific, they drag warm surface water westward. Over time, enormous amounts of warm water accumulate near Indonesia and northern Australia. The sea surface there becomes significantly warmer than regions farther east. In some places, the difference can exceed several degrees Celsius. That may not sound dramatic. It is. Water stores immense quantities of heat. A single cubic meter of seawater can hold more energy than most people realize. Now multiply that by an ocean basin stretching thousands of kilometers. The numbers become almost impossible to comprehend. The Western Pacific effectively becomes a gigantic reservoir of stored heat. Meanwhile, something very different happens near South America. As surface water moves westward, colder water rises from the deep ocean below. Scientists call this upwelling. It is one of the most important oceanic processes on Earth. Cold, nutrient-rich water ascends from depths sometimes hundreds of meters below the surface. Marine ecosystems thrive, fish populations flourish, entire industries depend on it. The Peruvian anchovy fishery, one of the largest in history, owes much of its existence to this phenomenon. Without upwelling, the region would look very different. The ocean would behave very differently, and eventually the atmosphere would behave very differently. Because warm water and cold water affect air in completely different ways. Warm water fuels evaporation, cold water suppresses it. Where evaporation increases, clouds develop. Rainfall develops. Storm systems develop. The atmosphere begins moving energy around. This creates a giant circulation pattern known as the Walker circulation. The name sounds technical. The reality is easier to picture. Imagine a gigantic conveyor belt in the sky. Warm, moist air rises above the Western Pacific. Rain falls across Indonesia and surrounding regions. The air then travels eastward at high altitude. Eventually, it cools and sinks over the Eastern Pacific. Near the surface, trade winds push the air back westward. The cycle repeats endlessly, up, across, down, back, a planetary breathing pattern. And for decades, this system remains relatively stable. Then something disrupts it. The trade winds weaken, at first perhaps only slightly, a small fluctuation, a temporary disturbance, but sometimes that weakness grows, and when it does, the entire climate engine begins changing. Imagine a giant conveyor belt carrying thousands of boxes every hour. Then imagine somebody slowly turning down the motor. The boxes continue moving, but more slowly. Some begin accumulating in unexpected places, others stop altogether. Soon the entire system behaves differently. This is essentially what happens during El Niño. As trade winds weaken, warm water is no longer pushed westward as effectively. The enormous reservoir of heat near Indonesia begins spreading eastward, like water sloshing across a bathtub or molten metal flowing across a giant mold. Heat migrates. The atmosphere follows. This movement is not subtle. During strong El Niño events, warm water can travel thousands of kilometers across the Pacific. Regions normally characterized by cooler temperatures suddenly become much warmer. The Eastern Pacific transforms. The Central Pacific transforms. Cloud patterns transform. Rainfall patterns transform. And because the atmosphere functions as a connected system, disturbances begin spreading outward. Meteorologists sometimes compare El Niño to dropping a stone into a pond. The Pacific is the pond. Weather patterns are the ripples. But even that analogy understates the scale. A better comparison might be altering the thermostat inside a building that contains every nation on Earth. Change the temperature in one room and neighboring rooms adjust. Change enough heat, and eventually the entire structure responds. That is the power of the Pacific. And during a Super El Niño, the amount of redistributed heat becomes extraordinary. The ocean is not merely warming, it is relocating energy on a planetary scale. This is where another common misconception appears. Many people assume oceans respond to weather. In reality, weather often responds to oceans. The atmosphere changes quickly. The ocean changes slowly. That difference matters. A thunderstorm may last hours, a heat wave may last days, an ocean temperature anomaly can persist for months, sometimes longer. The ocean acts like a giant memory bank, storing energy, releasing energy, influencing conditions long after the initial changes occur. Scientists monitor this process constantly. Across the Pacific floats an enormous network of instruments. Hundreds of specialized buoys measure temperatures, winds, currents, humidity, and atmospheric pressure. Satellites observe sea surface temperatures from orbit. Research vessels collect additional data. Supercomputers analyze everything. Every hour. Every day. Every month. Because detecting the early signs of El Niño is like monitoring a sleeping volcano. You may not know exactly when conditions will change, but you want as much warning as possible. One particularly important measurement involves sea surface temperature anomalies. An anomaly simply means a departure from average conditions. When ocean temperatures rise significantly above normal across key regions of the tropical Pacific, scientists pay attention. When those anomalies continue growing, concern increases. And when the warming becomes widespread and persistent, discussions of a strong or even super El Niño begin. But surface temperatures tell only part of the story. The real warning often exists below. Deep beneath the Pacific, gigantic waves of warm water move through the ocean. These are not waves visible from a beach. They are vast subsurface movements carrying enormous quantities of heat. Scientists call them Kelvin waves. Some stretch across thousands of kilometers. Imagine a hidden river of warmth traveling beneath the ocean's surface, invisible to casual observers, yet capable of changing global weather months later. These underwater heat pulses frequently play a major role in the development of powerful El Niño events. And when scientists detect particularly strong Kelvin waves, attention sharpens immediately because they know what may follow. The atmosphere and ocean begin feeding each other. Warm water weakens trade winds. Weaker trade winds allow more warm water to move eastward. More warm water further weakens the winds. The cycle reinforces itself. A feedback loop. A climate chain reaction. Once established, it can become remarkably powerful. This is why Super El Niño events are so difficult to ignore. They are not isolated weather anomalies. They are system-wide transformations. The ocean changes, the atmosphere changes, weather changes. The consequences spread outward across the globe, and all of it begins with something surprisingly simple. Heat. Not fire, not storms, not hurricanes. Heat. Heat stored beneath the Pacific, heat accumulating over months. Heat moving across one-third of Earth's surface. Because long before floods arrive, long before droughts arrive, long before records begin falling, the hidden engine beneath the Pacific has already started turning. And when that engine accelerates, the rest of the planet eventually feels it. A Super El Niño does not begin with a storm. It begins with silence. Not literal silence, atmospheric silence. The kind that only scientists notice at first, the kind that appears as tiny changes on graphs, satellite maps, and weather models. A subtle weakening, a slight hesitation, a shift so small that nobody standing on a beach would ever notice it. Yet that tiny shift can eventually alter weather across half the planet. Because the most dangerous phase of El Niño is not when it becomes visible. The most dangerous phase is when it begins. And almost everything begins with the trade winds. For thousands of years, these winds have been among the most reliable features of Earth's climate system. They blow steadily from east to west across the tropical Pacific. Sailors once depended on them to cross oceans. Today, climate scientists depend on them to maintain stability. Think of the trade winds as giant invisible hands. Every day, those hands push warm surface water westward. They maintain the Pacific's normal balance. They keep heat concentrated near Indonesia and Australia. They help to sustain the atmospheric circulation patterns humanity has come to expect. Most of the time, they perform this task without interruption. Then something changes. The hands begin to weaken. Nobody fully understands why every El Niño starts. Scientists know many contributing factors: ocean temperatures, atmospheric pressure, natural climate variability, complex interactions between sea and sky. But the Earth is not a machine built by humans. There is no master switch, no single button that triggers El Niño. Instead, multiple forces gradually align, and eventually the trade winds begin losing strength. Imagine a giant spinning wheel. For years it turns smoothly, then friction increases. The wheel slows, not dramatically at first, barely enough to notice. But once the slowdown begins, the entire system starts responding. That is precisely what happens across the Pacific. As trade winds weaken, warm water that would normally remain concentrated in the west starts drifting eastward. The Pacific's carefully balanced heat distribution begins changing. The atmosphere notices immediately, and then something remarkable happens. The ocean and atmosphere start talking to each other, not through words, through energy, through pressure, through heat, through motion. This conversation is known as the Bjerknes feedback. Named after meteorologist Jacob Bjerknes, it is one of the most important climate mechanisms on Earth, and it helps explain why weak El Niños sometimes become monsters. The process works like this. Trade winds weaken. Warm water moves eastward. Warmer eastern Pacific waters fuel additional atmospheric changes. Those atmospheric changes weaken the trade winds even further, which allows even more warm water to move eastward, which weakens the winds again. The cycle feeds itself, round after round, like a snowball rolling downhill. Except this snowball is made of ocean heat, and it spans thousands of kilometers. Scientists sometimes describe this as a positive feedback loop. Positive does not mean good. It simply means the process reinforces itself. And reinforcement can become dangerous. A microphone placed too close to a speaker creates a familiar example. A small sound enters the microphone. The speaker amplifies it. The microphone captures the amplified sound. The speaker amplifies it again. Within seconds, an ear-piercing scream fills the room. The original signal may have been tiny. The feedback made it enormous. Super El Niño behaves similarly. Small atmospheric changes become larger. Larger changes become stronger. Stronger changes reshape global weather. One of the earliest warning signs often appears in atmospheric pressure. Meteorologists monitor a phenomenon called the Southern Oscillation. This involves pressure differences between the eastern and western Pacific. Normally, pressure patterns support strong trade winds. During El Niño development, those patterns begin shifting. The pressure gradient weakens. The winds weaken. The feedback loop strengthens. Scientists track these changes constantly because pressure changes frequently provide some of the earliest clues that a major event may be developing. This is where forecasting becomes both impressive and frustrating. Modern science can identify many warning signs months in advance: ocean temperatures, subsurface heat content, atmospheric pressure trends, wind anomalies, satellite observations, computer models. Yet forecasting El Niño remains one of the most challenging problems in climate science because the Pacific is enormous and Earth's climate system is extraordinarily complex. Tiny differences can grow into major outcomes. Small uncertainties can produce dramatically different forecasts. Meteorologists call part of this challenge the spring predictability barrier. It sounds technical. The reality is simple. Forecasting El Niño during Northern Hemisphere spring is notoriously difficult. The climate system becomes less predictable, signals become noisier, confidence decreases. It is like trying to predict the path of a river while standing in dense fog. You know the river exists, you know its general direction, but precise details remain hidden. Then there are the Kelvin waves, the hidden messengers of the Pacific. Long before El Niño becomes obvious at the surface, enormous pulses of warm water often begin moving eastward beneath the ocean. These waves travel along the equator, invisible from above, silent, relentless, sometimes moving at speeds exceeding 200 kilometers per day. Imagine a gigantic underwater freight train carrying heat across the Pacific. Now imagine that train stretching thousands of kilometers. That is essentially what a Kelvin wave represents. When particularly powerful Kelvin waves appear, scientists pay close attention. because they often signal that significant warming may soon reach the surface. And once surface warming begins, the atmosphere can respond rapidly. This is why meteorologists become excited about numbers that most people never hear: a fraction of a degree, a pressure anomaly, a wind shift, a subsurface temperature reading. To the public, these measurements seem insignificant. To climate scientists, they can represent the opening act of a planetary event. History has demonstrated this repeatedly. Months before the massive 1997-98 Super El Niño became obvious to the world, scientists were already detecting unusual conditions beneath the Pacific. The hidden engine was accelerating. The atmosphere had begun changing. The feedback loop was strengthening. By the time the public recognized something unusual was happening, the process was already well underway. This is one of the unsettling realities of climate systems. Many of the most important changes occur before anyone notices. A drought begins before crops fail. A flood begins before rivers overflow. A wildfire begins before smoke appears on the horizon. And a Super El Niño begins before weather maps start looking strange. The atmosphere always gives warnings. The challenge is recognizing them. Today, thousands of instruments across the Pacific watch for those warnings. Satellites orbit overhead. Buoys drift across tropical waters. Research vessels collect data. Supercomputers simulate countless possible futures. Scientists search for patterns. They search for signals. They search for the moment when ordinary variability begins transforming into something larger. Because once the trade winds start dying, the process can become difficult to stop. The Pacific begins reorganizing itself. Heat begins migrating. Atmospheric circulation begins shifting. Weather systems begin changing course. And the world slowly enters a new climatic chapter. Most people never see the beginning. They only see the consequences: the flood, the drought, the heat wave, the failed harvest, the wildfire, the record-breaking temperature. But all of those headlines often trace back to a much quieter event: a weakening breeze above a tropical ocean. A subtle atmospheric hesitation, a moment when the giant invisible hands that normally guide the Pacific begin to let go, and when they do, the ocean starts rewriting the future. When most people hear the words El Niño, they think about rain, floods, storms, maybe hurricanes. What they rarely think about is heat. Yet heat is where the story truly begins. Because before a Super El Niño creates floods, before it reshapes rainfall, before it alters storm tracks, it releases something far more fundamental: energy. And energy has consequences. Lots of them. In fact, some of the hottest years in modern history have occurred during or immediately after major El Niño events. That is not a coincidence. It is physics. The atmosphere is a giant engine. Heat is its fuel. And during a Super El Niño, the Pacific Ocean starts delivering enormous amounts of that fuel into the air above it. To understand why, imagine placing a pot of water on a stove. As the water warms, molecules begin moving faster, evaporation increases, steam rises, like energy transfers from the water into the surrounding air. Now scale that process up, way up. Instead of a kitchen stove, imagine a section of ocean spanning millions of square kilometers. Instead of a pot, imagine an entire tropical basin. The amount of energy involved becomes almost incomprehensible. The tropical Pacific is one of the most efficient heat transfer systems on Earth. When sea surface temperatures rise, evaporation accelerates. More water vapor enters the atmosphere. And water vapor is not just moisture, it is energy storage. Every droplet carries latent heat. Think of latent heat as invisible cargo, energy hidden inside water molecules. When those molecules rise into clouds and eventually condense, that energy is released back into the atmosphere. The result is a powerful transfer of heat from ocean to sky. During a Super El Niño, that transfer intensifies. The atmosphere becomes loaded with additional energy. And once that energy enters the climate system, it does not stay neatly organized. It spreads globally. This is why global temperature records often spike during strong El Niño years. The ocean effectively opens a giant heat valve. Energy that was previously stored beneath the surface begins influencing the atmosphere directly. The entire planet notices. The numbers tell the story. The powerful 1997-98 Super El Niño helped produce one of the warmest periods ever recorded at that time. Then the 2015-16 event arrived. Again, global temperatures surged. Again, records fell. Again, scientists watched the climate system respond to a massive pulse of oceanic heat. The pattern was unmistakable. When the Pacific releases extraordinary amounts of stored energy, the atmosphere gets warmer, and warmer atmospheres behave differently. That is where things become complicated. Heat is not merely uncomfortable. Heat changes systems. Heat changes probabilities. Heat changes outcomes. A warmer atmosphere can hold more water vapor. In fact, for every degree Celsius of warming, the atmosphere can hold roughly 7% more moisture. That number may sound modest. It is not. Imagine increasing the carrying capacity of every storm on Earth, not by a little, but across the entire atmosphere. That is what warming effectively does. Storms gain access to more moisture, rainfall can become more intense, flood risks increase, the water cycle accelerates, and yet, paradoxically, drought risks can increase too, because a warmer atmosphere is thirstier. It evaporates moisture more aggressively, it pulls water from soils more rapidly, it dries vegetation more efficiently. In some regions, this means heavier rainfall, in others, deeper drought. And so the atmosphere becomes more extreme at both ends. This is one of the reasons Super El Niño events often seem contradictory. One country experiences catastrophic flooding, another experiences devastating drought. Both outcomes emerge from the same underlying process: energy redistribution. Heat is being moved. The atmosphere responds differently depending on local conditions. Think of it like turning up the pressure inside a complex network of pipes. Some pipes overflow, others run dry. The pressure affects everything, but not in the same way. The effects can become startling. During major El Niño years, some cities have recorded temperatures far above seasonal averages. Heat waves become longer. Nighttime temperatures remain elevated. Recovery periods shrink. Infrastructure comes under stress. Power grids work harder. Agriculture faces additional challenges. Human health risks increase. And unlike storms, heat often arrives quietly. No dramatic clouds, no thunder, no obvious warning, just a relentless rise in temperature. Hour after hour, day after day. Heat kills differently. Floods destroy visibly. Heat destroys invisibly. The human body relies on a narrow temperature range. When that balance is disrupted, danger escalates quickly, particularly for vulnerable populations. The elderly, young children, outdoor workers, people without access to cooling. History repeatedly shows that severe heat waves can become some of the deadliest weather events on Earth, not because they are dramatic, because they are persistent, and persistence can be lethal. Agriculture feels the impact as well. Plants are remarkably sensitive to temperature. A few degrees may determine whether crops thrive or fail. High temperatures increase evaporation from soil. Water demand rises. Growing seasons become stressed. Pollination can suffer. Yields can decline. A single heat wave arriving at the wrong moment can erase months of agricultural effort. Farmers understand this reality better than most because they live at the intersection of weather and survival. For them, climate is not an abstract concept, it is a daily reality. And when major climate patterns shift, the consequences can arrive quickly. Then there are the oceans themselves. The same heat that affects weather also affects marine ecosystems. Fish species begin migrating. Some move toward cooler waters, others experience population declines. Food chains become disrupted. Coral reefs face increasing stress, and few ecosystems illustrate the danger more clearly than coral reefs. Corals exist near their thermal limits. They thrive within specific temperature ranges. Push temperatures too high for too long, and bleaching begins. The coral expels the symbiotic algae it depends upon. The reef turns white. Its survival becomes uncertain. During major El Nino events, widespread bleaching has occurred across multiple ocean basins. Some reefs recover, others do not. Entire ecosystems can change. And because millions of people depend on reef systems for food, tourism, and coastal protection, the consequences extend far beyond the underwater world. What makes all of this particularly important today is the broader context. The planet is already warmer than it was during previous centuries. Ocean temperatures have reached remarkable levels in recent years. The atmosphere contains more heat, more moisture, more energy. Scientists continue investigating exactly how this background warming interacts with El Nino, but the concern is obvious. A strong El Nino occurring in an already warmer climate may produce outcomes that exceed historical expectations. Not because the laws of physics have changed, because the starting point has changed. Imagine two runners beginning a race. One starts at the starting line, the other begins 50 meters ahead. The race unfolds differently. The initial conditions matter. Climate works similarly. When the baseline shifts, extremes become easier to reach, records become easier to break, and the atmosphere gains access to additional energy. That energy does not remain idle. It powers storms, it fuels heat waves, it drives evaporation, it reshapes weather patterns. And during a Super El Niño, the Pacific Ocean acts as the world's largest energy distributor, a giant heat reservoir opening its vault. Most people will never see that process happen. They will only experience the consequences. The unusually hot summer, the oppressive humidity, the drought, the wildfire, the flood, the broken record, the strange feeling that the weather no longer behaves the way it used to. But behind every one of those experiences lies the same fundamental force: heat, invisible, persistent, planetary. And once the Pacific starts releasing enough of it, the atmosphere becomes something far more dangerous: a heat wave factory operating on a global scale. One of the strangest things about a Super El Nino is that it can create opposite disasters at the same time. One region floods, another dries out. One river bursts its banks, another shrinks into mud. One farmer watches fields disappear beneath water, another watches crops die from lack of it. At first glance, it makes no sense. How can the same climate event produce such different outcomes? The answer reveals something profound about Earth's atmosphere. Weather is not a collection of isolated events, it is a connected system, a giant machine balancing energy across the entire planet. And when a Super El Nino shifts that balance, every piece of the machine responds, just not in the same way. Imagine a gigantic waterbed stretching across the Earth. Pressed down in one location, the entire surface changes shape. Some areas rise, others sink. The effect spreads outward in all directions. The atmosphere behaves similarly. A major concentration of heat in one part of the Pacific does not stay confined there. It alters circulation patterns globally. Jet streams shift. Pressure systems move. Storm tracks relocate. Rainfall follows new routes. The result is a planet where familiar weather patterns suddenly become unfamiliar. This is where the real danger begins. Human civilization is built around expectations. Cities expect certain rainfall patterns. Farmers expect certain growing seasons. Reservoir managers expect rivers to behave in predictable ways. Governments expect weather to remain within historical ranges. A Super El Niño disrupts those assumptions, and assumptions are often what keep societies functioning smoothly. Take Peru and Ecuador. These countries frequently experience some of the most dramatic rainfall impacts during major El Niño events. Under normal conditions, portions of the western South American coastline are relatively dry. Cold ocean currents help suppress rainfall. But when warm Pacific waters arrive, everything changes. Evaporation increases, moisture surges into the atmosphere, storm systems gain fuel, rainfall can become extraordinary. Entire years' worth of rain may fall in just weeks. Rivers swell, roads vanish, landslides multiply. Infrastructure designed for ordinary weather suddenly faces extraordinary conditions. Now travel across the Pacific to Indonesia. The story reverses. As warm water shifts eastward, rainfall often follows it. Regions that normally depend on tropical moisture may suddenly find themselves deprived of it. Clouds become less frequent, rainfall declines, drought emerges, vegetation dries, water supplies come under pressure. Wildfire risk increases dramatically. The same oceanic event, the opposite outcome. Flood on one side, drought on the other. This is one of the defining signatures of El Niño. The atmosphere is redistributing moisture, not creating it from nothing. Some places receive more, others receive less, and the consequences can be severe. Australia provides another example. The continent already occupies one of the driest inhabited regions on Earth. Water has always been precious there. During strong El Niño events, rainfall often declines across large portions of the country. Temperatures frequently rise, vegetation dries, bushfire conditions worsen, farmers face increased uncertainty, reservoir levels can fall, the margin for error becomes smaller. Australia understands, perhaps better than most nations, that drought is not merely a weather event. It is an economic event, an ecological event, a societal event, because water underpins everything: food production, energy generation, transportation, public health. Remove enough water, and entire systems begin feeling the strain. Then there is North America. This is where things become especially interesting. The effects vary dramatically depending on location. A super El Niño often shifts the position of the Pacific jet stream. Storms that might normally track elsewhere are redirected. The southern United States frequently experiences wetter than average conditions during major events. California, in particular, often attracts attention. For years, drought can dominate headlines. Then a strong El Niño arrives. Powerful storms begin marching inland. Rainfall increases. Mountain snowpack grows. Reservoirs refill. At first, this sounds beneficial, and sometimes it is. But excessive rainfall introduces its own dangers: flooding, landslides, infrastructure damage, coastal erosion. The atmosphere rarely deals in moderation, especially when large amounts of energy are involved. The northern United States and parts of Canada may experience very different outcomes. Warmer winters often become more likely. Snowfall patterns can change. Cold air outbreaks may become less frequent in some regions. Yet even these broad tendencies come with exceptions. The atmosphere remains enormously complex. El Niño influences probabilities. It does not dictate certainty. This distinction matters because one of the biggest misconceptions about climate forecasting is the belief that it predicts exact outcomes. It does not. Meteorologists are not fortune tellers. They are probability experts. A super El Niño increases the likelihood of certain weather patterns, but weather always contains uncertainty. Think of a loaded pair of dice. The dice still roll unpredictably, but some numbers become more likely than others. That is how El Niño influences weather. It changes the odds, and when billions of people live under those odds, even modest shifts become important. Then there is Africa. The continent's relationship with El Niño varies enormously depending on region. Some areas experience enhanced rainfall, others face drought. Eastern Africa often sees increased flood risk during certain phases. Southern Africa frequently faces greater drought concerns. Agriculture becomes vulnerable, food security becomes vulnerable, water supplies become vulnerable. Because when rainfall patterns shift across regions dependent on seasonal precipitation, the consequences can extend far beyond weather itself. Harvests affect food prices. Food prices affect economies. Economies affect stability. Climate can become a force multiplier. A small environmental disruption can cascade through entire societies. The same applies in Asia. Monsoon systems influence billions of lives. Their timing matters. Their intensity matters. A delayed monsoon can affect planting schedules. A weak monsoon can affect harvests. An overly intense monsoon can trigger floods and landslides. El Niño frequently influences these systems, not always in the same way, not always predictably, but enough that governments monitor Pacific conditions with intense interest because they understand something important. A climate signal originating thousands of kilometers away may eventually affect the food supply of hundreds of millions of people. That is how interconnected the modern world has become. And perhaps that is the most astonishing aspect of all. A patch of warm ocean near the equator can influence a farmer in India, a city in California, a village in Peru, a cattle station in Australia, a river in Africa, a reef in the Pacific. The atmosphere links them all. The weather outside your window feels local. In reality, it is often part of a much larger story, a story involving oceans, winds, pressure systems, and heat moving around the planet. A story that humanity only began fully understanding in recent decades. And during a Super El Niño, that story becomes impossible to ignore because somewhere rain is arriving where it should not. Somewhere else, rain is failing to arrive at all. One community is preparing for floods, another is praying for clouds. One landscape is turning green, another is turning brown. The same climate engine is responsible for both, because when the Pacific starts redistributing heat, it also redistributes water. And water is civilization's most important resource. Too much of it can destroy, too little of it can destroy. A Super El Nino has the power to deliver both, often at the very same time. Most people think storms are random. A thunderstorm appears, a hurricane forms, a winter cyclone arrives. Weather seems chaotic, unpredictable, almost accidental, but the atmosphere is far more organized than it appears. Storms do not simply wander across the planet. They follow pathways, invisible highways in the sky, and during a Super El Nino, many of those highways begin to move. That is when familiar weather starts behaving in unfamiliar ways. That is when records begin falling. That is when forecasters start paying very close attention because a shifting storm track can change the fate of entire regions. To understand why, imagine standing on a mountain overlooking a major motorway. Thousands of vehicles travel along predictable routes. Cities depend on that flow. Businesses depend on that flow. Entire economies depend on that flow. Now imagine moving the motorway 50 kilometers north. Everything changes. New towns receive traffic. Old towns lose it. Supplies arrive in different places. The entire system reorganizes itself. The atmosphere behaves in a remarkably similar way. High above your head, powerful rivers of air circle the planet. Meteorologists call them jet streams. These narrow bands of fast moving wind can reach speeds exceeding 300 kilometers per hour. They help steer storms, guide weather systems, separate warm air from cold air, and influence conditions across enormous distances. Most people never see them, yet few atmospheric features are more important. The jet stream is one of the great architects of weather, and during a Super El Niño, it often changes position. The reason comes back to heat. It always comes back to heat. When large areas of the tropical Pacific become unusually warm, massive amounts of energy enter the atmosphere. That energy affects pressure patterns. Pressure patterns influence wind. Wind influences the jet stream. The jet stream influences storms. A chain reaction begins. And because the atmosphere is interconnected, changes near the equator can eventually influence weather thousands of kilometers away. Meteorologists sometimes describe this as atmospheric teleconnection. The name sounds complicated. The concept is simple. One part of the planet changes, another part responds. Imagine plucking a guitar string. The vibration spreads through the entire instrument. The atmosphere works in much the same way. A disturbance in the Pacific creates ripples that travel across the globe. The jet stream often carries those ripples. In North America, one of the most common El Niño effects involves the southern branch of the jet stream strengthening. Storm systems that might normally remain offshore begin moving inland. Rainfall increases across parts of the southern United States. California often receives significant attention during these periods. For years, drought may dominate the landscape, reservoirs decline, vegetation dries, water restrictions become common. Then a powerful El Niño arrives. Storm after storm begins crossing the Pacific. Rainfall intensifies, mountain snowpack grows, rivers swell, sometimes dramatically. The same atmospheric highway that once bypassed the region suddenly points directly at it, and that shift can make all the difference. But increased rainfall is not always good news. People often hear more rain and imagine relief. Nature is rarely that simple. A landscape hardened by drought can struggle to absorb sudden downpours. Water rushes across the surface. Flooding develops quickly. Mudslides become more likely. Infrastructure experiences strain. The atmosphere can deliver too much help all at once, and too much water becomes its own disaster. Meanwhile, other regions may experience the opposite problem. Storms that once arrived reliably begin missing their targets. Rainfall declines. Dry conditions persist. Drought deepens. The atmosphere is not creating storms from nothing. It is redirecting them, and redirection creates winners and losers. This is one reason Super El Niño events are so difficult for governments and planners. The challenge is not merely forecasting weather. The challenge is forecasting where the weather will go. Because location matters. A storm over the ocean is one thing. The same storm over a city is something entirely different. The same storm over farmland can determine whether crops survive. The same storm over a mountain range can trigger landslides. A slight change in trajectory can have enormous consequences. This becomes even more dramatic when tropical cyclones enter the picture. Hurricanes, typhoons, cyclones, different names, same underlying phenomenon, and El Niño often influences them as well. One of the most fascinating effects involves the Atlantic hurricane season. During many El Niño years, hurricane activity in the Atlantic tends to decrease. At first, that seems strange. If the atmosphere contains more heat and energy, shouldn't hurricanes become more common? The answer reveals the complexity of weather. Hurricanes require more than warm water. They require favorable atmospheric conditions. One of the most important is low wind shear. Wind shear occurs when winds change speed or direction with altitude. Too much shear acts like a giant pair of scissors. It tears developing storms apart, prevents them from organizing, disrupts their structure. During many El Nino events, upper level winds across portions of the Atlantic become stronger. Wind shear increases, the environment becomes less hospitable for hurricane development. The result can be fewer Atlantic hurricanes. Meanwhile, the Pacific may experience very different conditions. Storm activity can shift, storm tracks can shift, risk zones can shift. Again, the atmosphere redistributes probability, not certainty. Probability. And probability shapes outcomes. This is one reason climate scientists spend enormous effort studying atmospheric circulation.